Hey guys, welcome to the 5th video in the Simply AI series. Today, we'll be looking at other prominent fields of AI. Today, we'll be looking at various other fields of AI, such as computer vision, natural language processing, evolutionary computing, machine planning, and robotics. We will also look at some futuristic developments in AI. The main purpose is to introduce the names, big ideas, and provide a glimpse of some details. It's okay if you don't understand some of these details, as we'll cover them with more concrete examples and applications later on. Computer vision is an important field, as it allows machines to see and interact with their surroundings. We won't go into the various sensors and equipment that allows machines to obtain such sensory information, but we'll look primarily at how such information is processed. Computer vision is about deriving meaningful information from visual content like digital images, videos, and other visual input. Note that with the effectiveness of machine learning in recognizing visual content, such as with convolutional neural networks, there is a lot of cross-AI field technology overlap. Here, we will cover only the fields that are native to computer vision. Here are some of the important fields. Scene reconstruction involves reconstructing a digital version of a real-world object from visual content. Essentially, recreate a model from images. Object detection identifies objects in visual content. An example of this is detecting vehicles on a toll road. Object recognition is about finding and classifying objects in visual content. Motion estimation is about estimating the motion of an object in a visual sequence using techniques such as object tracking and optical flow. It allows a robot to avoid obstacles. 3D pose estimation is about estimating an object's current 3D orientation and predicting how an object would look based on a reference pose. Human 3D pose estimation has great real-world applications. Next, we visit natural language processing, or NLP for short. Say hello to Google Home and Siri. NLP enables machines to understand text and spoken words in human languages. The fields include text processing. Although one would assume NLP would be mostly interactive speedbots, the bulk of human information is in books and documents, and processing such documents is a big deal. Natural language processing is used heavily to process documents. Some outstanding applications include automatic summary, grammar correction, language translation, question answering, sentiment analysis, and the list goes on. Speech recognition recognizes what people are saying with speech bots like Google Home and Siri. Speech is converted to a textual representation that can be processed further either syntactically or after interpreting it into something useful. Speech synthesis converts text and symbols to speech. With speech recognition and synthesis, you have a machine conversing in natural language and performing its processing underneath using text. This is very powerful, as now you use the most natural interface to converse with humans and the most pragmatic interface to perform work on machines. Ontology engineering. Ontology comes up with tokens and associates a meaning to each token to be used for a specific purpose or scope. Ontologies enabled some very interesting advances in the semantic web, and they perform a very robust formal basis for knowledge representation in many pragmatic, real-world applications. NLP can be used to represent concepts of a domain into ontology, formalizing the name and its semantics, and effectively adapt to changes in the domain. Next, we visit evolutionary computing. This is an exciting area where many algorithms are modeled after biological evolution. Evolutionary computing attempts to perform global optimization using techniques similar to biological evolution, such as Darwinian principles of natural selection. Some techniques include genetic algorithms. Many possible candidates can exist in a population, and each is assigned genes based on some domain properties. Iteratively, these candidates undergo genetic operations like mutation, crossover, and inversion, like in real-world biological evolutionary processes. A fitness function is then used to optimize the population by weeding out weak candidates. The fitness function controls the expected outcome. What is optimized in the genetic operations attempt to ensure that all interesting combinations are visited. Mimetic algorithms. These algorithms are similar to genetic algorithms, but instead of genes, They're based on memes. A meme is an imitation of a cultural element and spreads within the population by imitation, not by genetic evolution. To account for the memes, the genetic algorithms incorporate additional local search components representing the memes. Differential evolution iteratively combines candidates using simple formulas with the goal of optimizing the problem with regard to a given measure of quality. Swarm intelligence involves decentralized, self-organizing agents following very simple rules while interacting with others in their environment, resulting in an intelligent global behavior. An example of this are ant and bee colonies. Neuroevolution is based on the fact that the structure of our brains, the number of neurons and how these neurons connect with each other, has evolved over millions of years. So instead of using a fixed structure of the network to simply learn by observation on how to correct errors, we use evolution to alter the structure and behavior of a neural network. It uses evolutionary methods to generate neural networks but without any error-based backpropagation. Instead of error-based backpropagation to learn the network parameters, it uses evolutionary methods to compute the weights and/or alter the net structure. Next, we visit machine planning. Automatic planning has been an area that would be a stepping stone for numerous autonomous applications. Moreover, the concepts of distributed multiple agents independently or collaboratively planning to meet a common goal has great real-world utility. A plan is a sequence of actions to be taken to meet a specific goal. Planning involves the following elements. A state captures possible situations that could arise, such as position or location, orientation, velocity, etc. Initial state is where planning begins. The goal state is where the planning ends, and essentially this is the goal of the plan. A plan is a sequence of decisions applied over time, with time being represented explicitly or implicitly in the chronology of actions. Actions manipulate the state and perform useful work. Criterion are constraints that the plan has to observe. The feasibility of a plan is to make sure things happen irrespective of the cost. Efficiency ensures feasibility while optimizing performance along certain aspects. Planning has different fields under it depending on the type of states, application, and conditions. Moreover, planning could be used for a single agent or coordinated across multiple agents. Discrete planning involves planning with finite or countably infinite state space. Continuous planning involves planning in a continuous state space. Numerous techniques here attempt to somehow reduce some or all aspects to make it discrete. Motion planning determines motions that are appropriate for a robot to reach a goal state without colliding into obstacles. Decision-theoretic planning is planning under uncertainty by overcoming unpredictability of current and future states. Differential constraint planning involves planning with local restrictions, such as velocity restrictions due to differential constraints, such as from kinematics and dynamics of robot motion. For example, instead of just planning to go from point A to point B, it is necessary to plan the velocity and acceleration at each point. And our final field that we'll look at today is robotics. The reason we look at it at the end is because robotics is more of an application of all the other fields. In fact, when it comes to AI, many fields involve concepts and techniques that are borrowed from other fields. The AI field of robotics deals with intelligence needed for a robot to properly function and optimize its operations. It does have a few aspects native to its field, but the majority of its intelligence challenges depend on other fields of AI. Its fields include sensing. The robot interacts with its environment with sensors, and intelligence is necessary to properly sense this environment, such as to improve accuracy and reliability to automatically detect errors and correct them. Actuation controls. A robot interacts with its environment using actuators, such as an electric motor, servo, and stepper motor. By proper control of an actuator, the robot is able to control its kinematics and dynamics that are so critical in performing its tasks. Robots today are replacing tasks which humans can't do, and to do so, you need excellent controls, better than what humans are able to have. Today, most precise brain surgery is performed by robots, as humans can't perform with that level of accuracy. And finally, navigation. In order for a robot to navigate in its environment, it has to analyze it in real time to ensure that it can avoid obstacles and optimize its motion by automatically adapting its speed and paths. If the robot is to mingle with humans in busy spaces, it also needs to be aware of the cognitive abilities of entities around it and be able to interact similarly. This field overlaps with numerous AI subfields such as computer vision, motion estimation, and motion planning. In addition to these fields, there are new areas of AI that are on the horizon, paving our way to the next types of intelligence. These include cognitive intelligence. Cognitive intelligence deals with intelligence needed to interact with humans naturally. This is paving the way to the next types of intelligence, such as the theory of mind, and may be used for self-awareness. Predictive analytics. Businesses use historical data and AI to identify the likelihood of future outcomes. Today, it still relies heavily on data mining, with a bit of machine learning making some headway. Many AI fields can make a big difference here. With advances in new fields like explainable AI, maybe we will see a more profound AI presence in this world. Federated learning. Data is pervasive, but unfortunately, it cannot flow freely due to the real-world constraints. This intelligence uses collaborative AI approaches that uses islands of data, but collaborates the intelligence while respecting the real-world norms. This can revolutionize the use of AI in a lot more aspects of our lives. Transformers. New techniques like transformers are effective for NLP and can be applied to other fields of AI like computer vision. Cross-AI application of promising techniques can significantly leapfrog our AI landscape. And finally, nanobots. The use of numerous tiny robots to perform targeted work inside the body can change medical treatments for numerous incurable diseases today. AI has a big role here. What is it, and how will it shape our future? The big question is, while this is happening, where will you be? My sincere hope is that I have motivated you in this amazing world of AI, pioneering our quest for a better tomorrow. So today, we have looked at various other fields of AI, such as computer vision, natural language processing, evolutionary computing, machine planning, and robotics, as well as looking at some futuristic developments in AI. Thank you very much for listening to this video, and I hope you'll join us for the next video, where we dive deep into naive Bayes. See you then!